Welcome to this explainer. Okay, today we are going to completely demystify matrices, breaking them down into really simple, easy-to-understand visual building blocks. If you've ever stared at a massive block of numbers and just felt kind of lost, honestly, don't worry. By the end of this, you're going to see exactly how elegant and incredibly useful this branch of math really is.
Here is our roadmap for today. We'll quickly move through 1. The matrix concept, 2. Anatomy and order, 3. The matrix family tree, 4. Diagonals and trace, and finally, number 5. Basic matrix operations. Let's just jump right in.
Section 1. The matrix concept. Let's ground all this theory into a relatable real-world problem, because math is always way easier to grasp when you see what it's actually doing for us. Imagine you're tracking the performance of 3 cricket players, Saqib, Tamim, and Mosh, and you've got their scores against 3 different teams, India, England, and Australia. Now, if we just scribble these numbers down randomly on a page, it's a total mess. But notice how arranging those scattered stats into a structured grid instantly organizes everything. The rows represent our players, the columns represent the opposing teams. This elegant rectangular array of numbers, neatly enclosed in brackets, is precisely what we call a matrix. Honestly, it's just an organizational superpower.
Moving on to Section 2, Anatomy, Order, and Notation.
Now that we see why they're useful, we really need to understand the basic anatomy of a matrix so we can actually use it. Think of it like architecture. Just like a physical building relies on horizontal floors and vertical pillars, every single matrix is structurally built on horizontal rows and vertical columns. So, whenever you look at a matrix, always train your brain to scan left to right first, those are your rows, and then top to bottom, those are your columns. It's literally the baseline for everything else we're going to do.
To even talk about matrices, we have to know their size, which mathematicians call the order or the dimension. Finding the order is incredibly straightforward, just 3 simple counting steps. Step 1, you count the number of horizontal rows, which we label m. Step 2, count the vertical columns, which we label n. And step 3, you just write it out as m times n. Out loud, we say m by n.
Let's bring back our cricket matrix to see this in action. Look at the groupings. We have exactly 3 horizontal rows holding our player data. Next, we count our vertical columns for the opposing teams. And yep, there are exactly 3 of those as well. So, following our quick formula, m is 3 and n is 3. That clearly establishes this as a 3 by 3 matrix. It really is just a matter of careful counting.
But what if you want to pull one specific piece of data out of that grid? To pinpoint a specific element, we use a clever little address system, written as A with a subscript of I and J. In this system, I is the row number and J is the column number. So if I ask for element A23, I'm basically telling you to go down to the second row and look across to the third column. It's exactly like finding your assigned seat in a movie theater.
All right, Section 3, the matrix family tree.
Now, what's really fascinating here is that matrices form an exclusive hierarchy, kind of like a set of VIP clubs. This flowchart perfectly maps out those mathematical clubs, and you can think of it as our visual anchor. At the top, we have the broad category of square matrices. Underneath that, it splits into triangular matrices on one side and diagonal matrices on the other, which then filter down into even more exclusive categories. We'll continually refer back to this family tree.
But before we hit the VIP clubs, let's look at the absolute simplest forms. On the left, we have the row matrix. It has one and only one horizontal row, though it can stretch out with as many columns as it likes. Its counterpart over on the right is the column matrix. That one stands tall, with exactly one vertical column and multiple rows. These guys are basically the structural building blocks for vectors.
Okay, here's the first major gatekeeper to our hierarchy, the square matrix. For a matrix to gain entry here, it must be perfectly balanced. The number of rows absolutely must equal the number of columns, an n by n order. Here we're looking at a 3 by 3 matrix, forming a perfect mathematical square. And just so you know, the vast majority of higher-level matrix math totally requires you to be inside this square club. Once you're inside the square club, you might qualify as a triangular matrix. Look at that diagonal line of numbers slicing from the top left to the bottom right. We call that the main diagonal. To be a triangular matrix, everything either strictly above that line or strictly below it must be completely zero. Notice how the remaining non-zero numbers physically form a triangle shape in one half of the matrix? Pretty cool, right?
Now, let's look at the other branch of our family tree, where the rules get a bit stricter. A diagonal matrix means every single number that is not on the main diagonal is 0. It's pretty relaxed about what numbers are actually on the diagonal itself. But to enter the more exclusive scalar matrix club, those diagonal numbers can't just be random. They must be perfectly identical to each other. Every single one has to match.
And that brings us to the most exclusive club of the whole bunch, the identity matrix, usually represented by a capital I. To get in here, you've got to be a scalar matrix, but the bouncer has one final very strict rule. Every single identical number on your main diagonal must be exactly the number 1. That's it. 1's on the diagonal, 0's everywhere else. In the matrix world, this behaves exactly like the number 1 does in regular, everyday arithmetic.
Let's pause for a quick second and actually test your understanding of this family tree. Based on the strict rules we literally just went over, how would you classify a 2x2 matrix that has 1's on its diagonal and 0's everywhere else? Take a moment. Think about it. Does it belong to just one club, or does it get into multiple? Well, if you deduce that it checks the boxes for all 3 categories simultaneously, you hit the nail on the head. It's a diagonal matrix because the non-diagonals are 0. It's a scalar matrix because the diagonal numbers match, and it's an identity matrix because those matching numbers are exactly 1. This brilliantly shows how these mathematical rules perfectly stack right on top of one another.
Moving right along. Section 4, Diagonals and Trace.
We keep talking about this principal diagonal. Well, mathematicians actually gave a special name to the sum of those specific numbers. They call it the trace. And honestly, finding the trace of a matrix isn't complicated at all. It is simply the sum total of the numbers lying directly on that main diagonal, reading from top left to bottom right. You literally just add them up.
Let's look at a typical way this might be tested. Say we have a 3x3 matrix, and the diagonal elements are 1, 4, and an unknown variable, a. But we are told up front that the trace equals 8. By setting up a super basic algebraic equation, 1 plus 4 plus a equals 8, we can easily work backwards. 1 plus 4 is 5, and 8 minus 5 reveals that our missing variable a absolutely must be 3. It's a simple trick, but incredibly powerful for solving for unknowns.
And our final stop, Section 5, Basic Matrix Operations.
Up until now, we've only looked at matrices in isolation. Let's finally bring multiple matrices together. Adding or subtracting 2 matrices is wonderfully intuitive. The only catch? The matrices must be the exact same size. If they are, you just match up the corresponding elements in identical positions and combine them. So the top left element A in the first matrix adds directly to the top left element 1 in the second matrix, giving us A plus 1. You just do standard arithmetic, slot by slot. And subtraction works exactly the same way. Okay, we've covered a lot. We've mastered the anatomy, the family tree, the trace, and basic addition. But I want to leave you with a bit of a provocative thought. If matrix addition is this straightforward, literally just matching up slots, will matrix multiplication follow that same easy, intuitive pattern? Or are we about to enter a completely different structural dimension where rows actively crash into columns? I highly encourage you to go find out. Thanks so much for joining me on this explainer, and keep learning.